Hello everyone, here in this section we have extreme values and saddle point. Definition: let f of xy be defined a region R containing the point a, b. Then here we have f of a, b is local maximum value of f if f of a b greater than or equal to f of xy for all domain points x, y in an open disk centered at a, b. Number 2, f of a, b is local minimum value of f if f of a, b less than or equal to f of xy. So here we have greater than or equal to, here we have less than or equal to. For all domain points x, y in an open disk centered at a, b. First derivative test for local extreme values. If f of xy has a local maximum or a local minimum value at an interior point a, b of its domain, and if the first partial derivatives exist, then partial derivative of f with respect to x equal to 0 and partial derivative of f with respect to y equal to 0, and it's in this point a, b. An interior point of the domain of a function f of xy where both partial derivative of f with respect to x and partial derivative of f with respect to y are 0, or where one or both of partial derivative of f with respect to x and partial derivative of f with respect to y do not exist, is a critical point of f. Here under definition, a differentiable function f of xy has a saddle point at a critical point a, b if in every open disk centered at this point a, b there are domain points x, y where f of xy greater than f of a, b, and domain points x, y where f of x, y less than f of a, b. The corresponding point a, b, f of a, b on the surface is equal to f of xy is called saddle point of the surface. Find the local extreme values of f of xy equal to x squared plus y squared minus 4y plus 9. The domain of f is the entire plane, so there are no boundary points, and partial derivative of f with respect to x and partial derivative of f with respect to y exist everywhere. So here we have partial derivative of f with respect to x that is equal to 2x, and partial derivative of f with respect to y that is equal to 2y minus 4. So we have local extreme values when partial derivative of f with respect to x it is equal to 0, and partial derivative of f with respect to y it is equal to 0. So here we have 2x equal to 0 and 2y minus 4 equal to 0. So the only point that we have here is 0, 2, and based on this point f of xy it is equal to 5. So f of 0, 2, what is equal to 0 squared plus 2 squared minus 4 times 2 plus 9 it is equal to 5. Based on what was given for f of xy, which is equal to x squared plus y squared minus 4y plus 9, this is equal to x squared plus y minus 2 squared plus 5. And based on what we have here, this is never less than 5. So we see that the critical point 0, 2 gives a local minimum. Second derivative test for local extreme values. Suppose that f of xy and its first and second partial derivatives are continuous throughout the disk centered at a, b, and that partial derivative of f with respect to x is equal to partial derivative of f with respect to y, and that is equal to 0, and this is based on this point a, b. Then f has a local maximum at a, b if partial derivative of f with respect to x and again x. So here we have second derivative is less than 0 and partial derivative of f with respect to x. So here we have second derivative with respect to x, and here we have partial derivative of f with respect to y and again y. So here we have second derivative minus. Here again we have second derivative and is partial derivative of f with respect to x, y. Here we have this power squared. This is greater than 0 at this point. So here we have f has a local minimum at a comma b if partial derivative of f with respect to x greater than 0. So here we have second derivative, and here again we have partial derivative of f with respect to x, and again x times partial derivative of f with respect to y, and again y minus partial derivative of f with respect to x, and again with respect to y, then squared greater than 0 at this point a comma b. So here we have second derivative, and here again second derivative. F has a saddle point at a comma b if second derivative with respect to x multiplied by second derivative with respect to y. So here we have partial derivative of f with respect to x, and partial derivative of f with respect to y. So here we're going to find first derivative with respect to x, and again we will find with respect to x, so second derivative with respect to x. And here on this part we have first we're going to find first derivative with respect to y, and again we're going to find the second derivative with respect to y minus f, so partial derivative of f with respect to the first one it is x, and then for second derivative we have with respect to y, and here we have square. So this one less than 0 at a comma b. And then here the test is inconclusive at a comma b if this one instead of less than 0 greater than 0, if this one y is equal to 0, so equal to 0 at a comma b. So partial derivative of f with respect to x, and again x, times the partial derivative of f with respect to y, again y, minus partial derivative of f with respect to x, and then with respect to y squared equal to 0. So here we have second derivative times second derivative minus second derivative. In this case, we must find some other way to determine the behavior of f at a comma b. The expression partial derivative of f with respect to x, again x, times partial derivative of f with respect to y, and the second derivative with respect to y, minus partial derivative of f with respect to x and second derivative with respect to y squared is called discriminant or Hessian of f. It is sometimes easier to remember it in determinant form. So here this is equal to this form determinant. So on the first part here we have fxx, here we have fyy, and this one is fxy, and here is fxy. Now here example, find the local extreme values of the function f of xy equal to xy minus x squared minus y squared minus 2x minus 2y plus 4. The function is defined and differentiable for all x and y, and its domain has no boundary points. Therefore, the function has extreme values only at the points where partial derivative of f with respect to x equal to 0 and partial derivative of f with respect to y equal to 0. So here we have partial derivative of f with respect to x is equal to y minus 2x minus 2, and here partial derivative of f with respect to y is equal to x minus 2y minus 2. Based on what we have here for partial derivative of f with respect to x and partial derivative of f with respect to y, finding x and y. So here I multiply the first one by 2, so here we have 2y minus 4x minus 4 equal to 0, and we have x minus 2y minus 2 equal to 0. So here adding, we can cancel this part. 2y minus 2y, it is 0. And then we have negative 4x plus x, it is negative 3x. Negative 4 plus negative 2, it is negative 6. And this is equal to 0. Solving for x, x is negative 2. And then use this negative 2 here in either the first or second. And plug in x. Here we have y minus 2 times negative 2 minus 2 equal to 0. Solving for y, it is negative 2. So here we have x equal to y, and that is equal to negative 2. Therefore, the point negative 2, comma negative 2 is the only point where f may take an extreme value. So here we have second derivative of f with respect to x based on what we have here is equal to negative 2, and second derivative of f with respect to y based on what we have here is negative 2, and second derivative of f with respect to y, so based on what we have here, because here we have f and here is partial derivative of f with respect to x first, then second derivative is x with respect to y, so here we have based on what we have on this part, so this is equal to 1. Now the discriminant of f at a comma b, which was equal to negative 2 comma negative 2, it is equal to negative 2, so this one is negative 2 times negative 2 minus what we had here is 1, so here we have 1 squared, and this is equal to 4 minus 1, so it is equal to 3, which is greater than 0. So here we have partial derivative of f with respect to x, and again x, this was less than 0. Based on what we had here was negative, and based on what we had here, this is greater than 0. This means f has a local maximum at negative 2 comma negative 2, and f of negative 2 comma negative 2, it is equal to 8. Find the local extreme values of f of xy equal to 3y squared minus 2y cubed minus 3x squared plus 6xy. Since f is differentiable everywhere, it can assume extreme values only where partial derivative of f with respect to x and partial derivative of f with respect to y equal to 0. So here we have partial derivative of f with respect to x equal to 6y minus 6x. Partial derivative of f with respect to y, it is equal to 6y minus 6y squared plus 6x. So from first equation, we have 6y equal to 6x, so that is same as x equal to y. And then substitute for y into the second equation, which is this one. So here we have, instead of y, we're going to use x. So it is 6x minus 6x squared plus 6x equal to 0, or 6x times 2 minus x equal to 0. So what I did here on this part, we had like terms. So here we have 12x minus 6x squared equal to 0, and then we had common factor between these two terms, and that was 6x, so factor of 6x, and here we have 6x times 2 minus x equal to 0. So solving for x, here we had x equal to 0 and x equal to 2. Because of having x equal to y, critical points are therefore 0, 0, and 2, 2. Now to classify the critical points, define the second derivatives. So here we have second derivative of f with respect to x equal to negative 6, second derivative of f with respect to y equal to 6 minus 12y. So here we have we used this equation, which was based on x for first derivative, and then here we used this equation, which was based on y. So first derivative was with respect to y. Then finally here we used the first equation on this part, which was with respect to x, but here second derivative is with respect to y, and that is equal to 6. Now the discriminant is negative 6 times 6 minus 12y minus 6 squared. So here, simplify, we have 72y minus 72, factor of 72, so this is equal to 72 times y minus 1. The critical point 0, 0, the value of discriminant is negative, so here we have negative 72, so the function is a saddle point at the origin. And at the critical point 2, 2, the value of discriminant is positive, and this is equal to 72. And based on what we had for second derivative of f, here the first derivative of with respect to x and the second derivative with respect to x, this was equal to negative 6 and this is negative number. So because of having this and this one, so here we have positive, discriminant is positive, and here we have negative. So the critical point 2, 2 gives a local maximum. And the value of f at this point is equal to 8. So here we have f of 2, 2 is equal to 3 times 2 squared minus 2 times 2 cubed minus 3 times 2 squared plus 6 times 2 times 2. So this is equal to 8.